Alright, hell yeah. So we have dynamics, and this is going to be a tricky subject. So we got motion relative to a rotating reference frame. You know what I mean? You have kind of like 3 or 4 things, at least 4 things part of this equation that are going on. And so we're going to tackle a starred problem. It's right here. And man, it's just kind of cool. I dig how like a ladder up against a wall, like falling. This one's on a step, so it's going to, and it's going this way. So this thing is going to go vertical. And so someone said, hey, what are the different ways you tackle problems? Because I don't actually know how to do this problem using the textbook. And textbooks are difficult. You almost need to pay for a professor just to sit down with you to explain and then re-explain things. But because, I don't know, just but all textbooks have sample problems, so you can kind of just copy-paste, but you're not really learning anything. I'm not. So my method is to see if I can do a problem in potentially the simplest way. And so for this one, we have, it wants to know, yeah, it's good to know what they actually want. Oh, and actually, I've only solved for one of the parts. But anyway, so they are going to call the point B on this, let's say it's just a ladder, but that's not this corner, you know what I mean? So I maybe call this corner like B naught, if you wanted a reference to where that is. Okay, so, and then this is going to be moving with a constant speed. So in just a little bit, this thing's going to be there, and then this whole ladder is going to be like tilted up, and then this point B is going to be moving up the ladder. And the first thing that I did to actually visualize that is just do kind of like small little drawings. Here's 2 feet. Let's get a visual on this. If this is 2 feet, they're saying this angle is 30 degrees. What we know about 30-degree angles is that the hypotenuse, this will be half the hypotenuse. So we know that this is 4 feet. So that's kind of what I did just right off the bat. And then if I said this was 4 feet, in the vertical position, you're going to have 2 feet and then 2 feet. So hell yeah. And so, and that's disregarding the end. This problem really doesn't need the end of this rod because this length is unspecified. Okay, so, and so when this goes vertical, yeah, that's kind of the first thing. Hey, point B is up there, and it's 2 feet higher. Okay, so let's look at the speed of this. This is going with a speed of 2 feet per second. We need to know this distance, and honestly, the first thing I did is I just guessed. You know, even with an angle of 30, we think that's pretty substantial, but this distance right here, you can just guess it's 4. So even just doing that, you know, and then can't you see it? It's like, hey, this is about 4, these are about 4. They're about even. And as this angle is much less, for sure, the hypotenuse is very similar. But it's not. This is 86.6% because cosine of 30 is 0.866. We'll get to that in a second. But the first thing, honestly, the first thing I did with this problem is just, hey, stand it up totally vertically. And then if we have a velocity of 2 feet per second, this point is going to get here in a time of 2 seconds. So we have a time of 2 seconds. And in 2 seconds, this point B, you know what I mean, where it initially was, travels 2 feet up. Okay, and so that's how I took something very complicated and at least did something with it. Now, every physics problem has like a, you know, this wants to deal with position, velocity, and acceleration. And so this probably shouldn't be your first rodeo with a starred problem, but there are some basics that you're going to take, you know what I mean? So one of the basics is kind of the definition of velocity, you know what I mean? Hey, definition of velocity is change in position, change in time. Same thing with acceleration. That's going to be change in velocity, change in time. So let's do it for this position at B. We're going to have a change in position. We're going to go from there to there. So we're going to have a change in position of 2 feet, and we did that in 2 seconds. So we have a velocity of 1 foot per second in this vertical direction. Okay, sweet. It says, honestly, the first place I took this problem, even though this is just totally wrong. You know what I mean? It's a horrible way to interpret like the actual answer. But it's fascinating because it takes one extreme, and then so the other extreme will be, well, I don't know if this, yeah, I guess that you could call this an extreme. But now we're going to take a look at, so that the next thing I did is just kind of drawed it out to scale. And then said, well, hey, let's take it halfway. So that's the second thing that I did. All right, hell yeah. So now when, and I kind of just, you know, I assumed this was kind of 4, and then we're going to say, hey, maybe, you know, just draw them about the same. So I'm going to go there, I'm going to go there. So that's the other thing, just like when you do drawings, try to make them to scale. And then I'm going to say B is there, and I'm going to say B is there. See how I just guessed? Sweet. So now this might be a better representative. And even the fact that I have these kind of in line, you can see that B was right there, B used to be here, and now B is up there. So right here I can totally see that, you know, like, hey, if this was the initial position and this is the final position, that's the other thing that's kind of interesting about learning about velocity from a positional standpoint, is right here we just said, hey, our initial position was there, our final position was there. This was the direction of our velocity. Like, basically, we are totally guessing that our velocity has this going upward. You know what I mean? So here, if our initial position, I'm just going to actually call it B naught, is right there, and then our next position is right there. That is, you know, if we drew our velocity vector, it would just be like that. It's in the direction of the initial to final position. That's the direction of our velocity. Okay, but hell yeah, that's all you get. You know what I mean? You get that direction of velocity. What we're not going to be able to tackle is the acceleration component. But we kind of will. And then that's gonna be kind of the second part that we're gonna kind of feel out. All right, hell yeah. And you know, and then you still want to be in like guessing mode. So we're just gonna say this was 2 feet, and we went 2 feet. The time was gonna be 1 second. Sweet. So we went from here to there in 1 second. And now we need some dimensions on this. Well, I'm just still gonna call this 2 feet. I'm gonna call this 2 feet. So this is a little bit more than 2 feet. And so if this total distance was 4, so now this is going to be a little bit more than 2 feet. So this maybe is just 1.5. You know what I mean? Let's say this is 2.5 and 1.5. Hell yeah. So now we know that our change in position, let's say it's just 1.5 foot in 1 second. So now maybe we have a better representative of our velocity. We're going to say our velocity, sorry, this is going to be velocity is change in position, change in time. So our velocity is going to be 1.5 feet per second in that direction. So we're going to say it's going that direction. Okay, hell yeah. So that was a pretty good representative, you know, of what was going on. And let's do it on this drawing. And so we're going to go here. We're going to, I'm just going to draw this line just to get a feel for how long this is. So I'm going to go from there to there, and then I'm going to go from there to there. Alright, booyah. Alright, I think those are about representative, and then I'm going to say this is 4, and then I'm going to say this is 4. So booyah. And you know, you can get a little bit tricky. You know, you can be like, and there's no reason why you can't do this. This is also like first, like hopefully this is kind of drawn to scale. And like it's drawn to scale as long as this angle is 30, and I believe it could be. So we're gonna come in here and we're gonna be like, hell yeah, there's 1, 2, and then we're gonna go 3, 4. Okay, booyah. So point B is just right up there, and let's double check this just to make sure. Yeah, hell yeah. And again, yeah. So this angle is pretty close. This angle is 30, so it is drawn to scale. I'm going to say, hey, there's our point B. And now we can kind of, well, one is that we can get, we can get the dimensions on this. So hey, we were pretty close with 1.5. You know, and so good enough. We're just going to call it right there. All right, but from this, now we have something that's kind of interesting. We know the velocity vector is in this direction. So this is our direction of our velocity vector. And it's at a higher angle than our ladder. Okay, sweet. So then I went to another extreme that I always know to go to. Like, let's make this ladder hella long this way. So we're just going to have a really big run-in. And then we're going to say, hey, this is 2 feet. That's our step. And I drew it way too long. But that's all right. And so when we have this, and now let's say, and this is our point B. So now let's say we take this, you know, like that 1 foot in. Or, you know, 2 feet, or whatever distance. But just a small distance there. And so now this is our angle. So now that you can see, hey, our point B was, our B naught's right there, and then we are basically going to travel this change, you know, this change in, I'm just going to call it change, well, let's just call it change in X. So this change in X is very similar, there to there, there to there. So it's these are basically equivalent, and then our new B is going to be right there. Sweet. But you are going to have a slight angle difference, but I guess don't worry about that. The whole reason to do this is just to show you that, hey, if this angle is really small and this is hella, you know, because this is hella far away, when we move this, you know, a small amount, this position B is, the vector is just going to go along this ladder. Now it is going to be a little bit higher, but you can just say, hey, the velocity is just along the ladder. So that's kind of the first thing of these ladder problems that, heck yeah, you should notice that maybe it goes along the ladder, and I think the second thing to pick up that it's also going to have an upward component too. Alright, hell yeah. So now we're going to start doing this problem kind of more 100%, and we have to see what it actually asks. It does not want a velocity vector. Well, this is the direction of the velocity vector if we just have a coordinate system, you know, x, y. But they want a coordinate system that's I'm going to call it x prime, y prime. They want to know the velocity in the direction of the ladder currently and the velocity this direction. And so let's redraw this, you know what I mean? Because I think we did a pretty good job. We're going to come in 1 foot here. Well, let's see. Alright, hell yeah. No, we got this. So yeah, now we'll get just a little bit more fancy. We're going to come in, oh man, messing this up. Okay, so we're going to come in 1 foot here, and then I'm going to draw, and I guess I'll just, this is, 105. So I'm going to come in here. I'm just going to draw this line to 105. So this is our point D. Now I'm going to come in on this. Oh, yeah. This is 1, 2, 3, 4. Okay, hell yeah. So, man, and because this is a line, you have to say that point B was right here, and now point B is right there. And initially, this ladder, you know, isn't three-dimensional. It's basically just this line. So this line is going to be kind of our x prime axis, and then we're going to draw 90. This is going to be our y prime axis. And you can see that this is our new B. You know, this is B at time 1. We'll just call it B prime. And then we have an angle in here. So this is going to be our change in angle. And, you know, so we'll definitely want to find that. But even right here, you know what I mean, hey, this is going to be 1 foot, so this is going to be like a half a foot, a quarter of a foot. And so we can come in here and get these dimensions. So where this is, it looks like this is going to be a half, you know, let's say 1, 2, 3, 4. Oh man, I don't know why I'm messing this up. But it looks like this is going to be like 0.8, 0.8 feet, sweet. And it's going to be up, not 0.2, maybe 0.2. Yeah, you know, maybe. So it might be up 0.2 feet. Okay, hell yeah. So now we have the velocities, because it asks, like, hey, what are the velocity components parallel and perpendicular to the bar? So we did this in 1 second. We traveled 1 foot. No, holy Toledo. My bad on this. And hopefully I didn't mess up the other one. So, yeah, we probably messed up this 1 foot per second. It travels 2 feet a second. Oh no, in this problem we went 2 feet. Okay, so right here we only went 1 foot. You know what I mean? So I should have made this bar right to here. Let's draw that one in. You know, just so we can kind of see the difference. And we need 2 points anyway, so this is going to be pretty sweet. So we're going to go up to there. That's our point D. And then I'm going to go 1, 2, 3, 4. So, oof. I don't even know where halfway is. Yeah, I guess that's halfway. Okay, hell yeah. So we got 1, 2, and then 3, and then booyah. So there is our B double prime. So well, I guess this is a half a second, and then this is another half second. So keep that in mind. But you can see that this, you know what I mean, we can bring this down, and it looks like we traveled this way. So in 1 second, we traveled that much this way, and then that much this way. You know what I mean? And so let's just guess. Hey, it looks like we traveled 1.5 feet a second. So we had a velocity of 1.5 feet per second that way, and then we had a velocity of 0.5 foot per second that way. You know what I mean? So there you go. So we took in 1 second, this thing moved 2 feet, so that was pretty easy. We get up to here, and we see that we move a 1.5. So we're kind of done. You know, just it's good to just be able to be like, hell yeah. So we're going to have 1.5 feet per second in this, I'm just going to call it I hat prime, plus, you know, because this would be your I hat direction, and this would be your J hat. But I'm going to call it the prime direction just because this, you know what I mean, this original direction, if we want to choose to use it, this is going to be our I hat, J hat. Okay, hell yeah. And then what did we say? Plus 0.5 feet per second, J hat prime. Alright, so there's going to be our velocity vector. And the overall velocity is just going to be the square root of 1.5 squared plus 0.5 squared. And we can do that. 1.5 squared plus 0.5 squared. And so we have a velocity of 1.58 feet per second. So that's an absolute magnitude. I'm going to do the vector, absolute value, and then booyah. Alright, so right there we have kind of our first guess on velocity, which is pretty sweet. And this problem is way cool because I didn't realize that, holy Toledo, you can guess like this. We should be doing more of this in physics and statics and dynamics. That's what this is. Because I was gonna do this life size and actually get the points. And sometimes that takes like a half a day to print all that stuff out, and you know what I mean. So this is just kind of fascinating. I really wasn't expecting to actually do this to get really accurate answers, but we can because now we have the other velocity vector. So this is double prime, but in a half a second, velocity vector at prime is what did we say? We said we were going to go 0.8 feet. So we're going to go 0.8 in the I prime direction, and then I really don't want to call this I prime anymore at all, but yeah, I think you get it. So we have 0.8 I hat plus 0.2 J hat, and the units on this are feet per second. Hell yeah. So that's going to be our other velocity component, or our velocity. So in a half a second, this is our velocity. In that second half a second, you know, from half a second to 1 second, this is our velocity. And so we do have a change in velocity because you can, well, oh, my bad. I don't even know. Yeah. Huge mistake. I make this mistake all the time. This is just the position. Like obviously this has nothing to do with velocity. These were just the positions. Yes, 1.5 feet and then up 0.5 feet. But we said we did it in a second, so it's also like the, you know, sure, the velocity, if you just got this point and it took 1 second to get there, yes, this velocity could check out, but we're actually not going to use it. So let's go back to, and I wrote this wrong. This actually, well, no, this was the same thing, sure, but this was wrong though. Because we did this distance in a half of a second. We would actually have to divide by 0.5, which is the same thing as multiplying by 0.2. So 0.8 goes to 1.6, and you can see that's very similar to this 1.5. 0.2 goes to 0.4, which is very similar to this 0.5. So it's kind of cool to make mistakes. So now we're going to try to take these points and then kind of do it more legit. All right, hell yeah. So let's take that first point, and we're going to call it B prime. So this is the vector, kind of a distance vector. I mean, this is our origin, so we're going to go 0, 0, and sweet. And so this is going to be 0.8 I plus 0.2 J, and this is in feet. And then we have that B prime, B double prime. So in 1 second, we're at a distance of 1.5 I plus 0.5 J in feet. And then we have, I'm just going to call it B naught. And this is going to be 0I plus 0J feet. So for these problems, this is my method. Any velocity acceleration, you know, this kind of goes back to the basics. And I mention this because, like, hey, if I come back to this problem 20 years from now, like, this is what I'm going to remember. I'm probably not going to remember anything else, but I do know that the definition of velocity is change in position, change in time. I know the definition of acceleration is change in velocity, change in time. And if I have 3 points, we can do this. And so what I typically do, yeah, let's explain this. So let's go out 30 millimeters to this point, and then we're going to go only 20 millimeters, and we're going to dot 20, and then we're going to go up like 10 millimeters, because this is very representative of maybe how things are. So this is the 0.0. This is going to be maybe after 1 second, and then after 2 seconds. And so, and then I'm just going to put a ghost point here. I'm going to call it like 2 prime. So let's say we had something moving from here to there, and we got a velocity, let's call it 10. Like 10, let's go back to metric, 10 meters per second. All right, hell yeah. So now, just visually, if we got here in a second, and it took another second to get here, what would be the velocity right there? You can just visualize it. If this is 10, this maybe looks like 6 or 7. We'll just call it 6. So our phantom velocity right here would be 6 meters per second. But we're going to say, hey, our particle got up to here. You know what I mean? So this is where it actually went. And so now you can get the absolute velocities. So this is going to be, we're going to call this absolute velocity. So we have 10 meters per second. And then maybe this, you know, if this looks like 10, this looks like 7. So 7 meters per second. Okay, hell yeah. And then let's play that game where you're just like, well, if this is 7, this looks like about 6. And if this is 7, this maybe only looks like 3. So we have, so there you go. We have some components. Wow, bummer. I really didn't even want to do that. You know what I mean? I really wanted to, so let's get this totally fresh. I wanted to say this, like, hey, we knew that this distance was greater than this distance. So if we come in with a speed of this, and then in this next second we have to slow down, that means we have an acceleration in that direction. That was this whole point of this diagram, to show what acceleration is. Because if we're coming in with this velocity, like if we're changing position there to there, you can totally see that that's going to be the velocity vector, and the velocity vector is like this long, you know what I mean? And then coming in here, that we're going to have a velocity vector that's only this long, you know what I mean? So if we hit this point, so we're going to have a slowdown of whatever this is, a car or whatever, and then, you know, in this direction, you know what I mean? So that's, and then what we do is we only work kind of in Cartesian directions. So this is maybe x and y, so we can see in the x direction we're going to have a slowdown. We're going to have an acceleration that way. But now we go look up at this point. And this is kind of the cool thing with 3 points, is because it can show you why there's acceleration when you have like a curved particle. Because obviously maybe this particle is like doing a curve here. And just to spell it out, you know, things want to stay on a straight line. But if you do curve them, the only way to stay on to make a particle go in a curve is to like force it that direction. So you're going to have to apply a force, and it's centripetal, you know what I mean? So there's 2 different words here. One is, and I can even, yeah, I'm getting better at this, centripetal. That's probably the harder one to like remember, but centrifugal, like a centrifuge. You know, when you do your blood samples, you know, in the circular deal, and then put the cap on, it spins around. All the, you know, and I guess all these are slanted this way. So, you know, it separates the blood. You know what I mean? So that's centrifugal. But this is, when things are spinning, they want to fly to the outside. You know, when things are spinning, they want to, like particles want to go into a straight line. So if you do have something spinning, the particle is getting kind of pushed to the outside, you could say. That's the centrifugal part. But if you look at it from the other direction, if I'm trying to take this car and actually make it do a curve, I would actually have to, like, you know, kind of put a hand of God on it and kind of push it along this curve from the outside in. So to keep anything going in a curve, you have to put a force on it. It doesn't matter if it's pushing or pulling. You know, you could pull on it like a rope. And the cool thing about gravity is, you know, like if this is the Earth and then we're on the outside, we're getting or like the sun and the Earth. Hey, like gravity is like a rope pulling you in, but that force is going to be that centrifugal force. It's good to mention that because if you have a force, you have acceleration, and so we bring in F equals ma. We have a force centripetal, and on that mass, that's kind of what we're analyzing, we must have an acceleration. Anytime that you have a force on a mass, you know, if you have a force on a mass and there's no other force to balance it, you have to check for that balancing force. But if you don't have that balancing force and you have a net force on a chunk of mass, it's going to accelerate. It's going to change its velocity. It's going to change its velocity in a change in time. So for hella sure, it's definitely going to change its position in a change of time. And you're going to get something like this, maybe like faster to slower, or you could be faster to even faster, you know what I mean? All right, hell yeah. All right, let's draw our points again, because still I wanted to show this point, you know what I mean? So we have the dot, 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 and we're going up here. So again, we're this speed, and then this speed in this direction, we're going to have an acceleration that way. That's going to be the acceleration in the x. So this is the cool demonstration on this. If a particle goes, if a car goes from here to there or whatever, it's going in that direction. You know what I mean? It's got a velocity in that direction, and that direction only. You know what I mean? So in this second, if that's exactly what we have, that's the only thing that we have. But in the next second, we traveled this perpendicular distance, and the fact that we did that So I like to say, hey, our velocity component in this direction is 0. We just don't have it. But over here, we changed our position in that direction. So we must have had a velocity component in this direction. And this can really help you with problems, because if you didn't have any velocity in this direction and you changed your position, let's just say this is the change in y, and this took a second to, well, I don't think I want to get into that right now, but basically the velocity at this point has to be 2 times, this velocity has to be like 2 times the average velocity. Because if you're just like, well, like what would be the average velocity? We do that with the little hat. The average velocity, because we went from here to there in a second. So we traveled this distance in 1 second. So our average velocity would be that distance, that's change in y in 1 second. So you can see that this is our average velocity, but we had no velocity, you know what I mean, at this point, and then we got there. So at this time, we must have had our velocity is 2 times the average. So, man, it probably wasn't a very good explanation. Well, especially if you're not like working on a problem where that's necessary, but that definitely comes up. All right, hell yeah. But let's draw that again, because I think one of these is not hidden and the other one is hidden. You know what I mean? And this happens when we talk about velocity and acceleration. With the acceleration equations, there's 2 that I consider hidden. One is just the fact that things go up in a circle, want to go in a straight line. Over here, if something's going around a circle, it wants to go just in a straight line, but the fact that it did, like again, we have to have that force centripetal. It had to move in that direction towards the center. You know what I mean? So it is a radial acceleration. We call it a normal acceleration. So the acceleration centripetal is a normal acceleration, and that's r omega squared. But regardless of that, it's you didn't have any velocity towards the center. All your velocity is tangential. Your velocity towards the radius or in the normal direction is 0. But then 1 second later, you popped up here. You kind of popped towards the radius. You're closer towards the radius here than you would have been out here. And so that distance that you travel, that's going to be, you know, I mean, change in r, change in y, or whatever. Hell yeah. So your velocity towards the center is going to be, 2 times the average. And, just the fact that you, and that's going to be your acceleration. Your acceleration in the normal direction is the change in velocity, change in time. The change in velocity is that 2 times the average, because that's where you could make a very big mistake and just call it, it's like, oh, well, we must have, just called it the average velocity divided by the change in time. But we could say it's 2 times that average velocity divided by, let's say, a second. You know what I mean? So, booyah. All right, hell yeah. So that's the crazy thing about the equations, is you have to know like what circles are, and you have to know that you have a centripetal acceleration because things want to go in a straight line, but somehow you move towards the center of the circle and you're a mass, and you must have had a force towards the center, and we're going to call that, and if you had a force, F equals ma, so if you have a centripetal force, you must have had a centripetal acceleration. You must have changed velocity in that direction. That's kind of what we're saying. But it's just way easier to be like, oh yeah, no duh. Like I definitely see that I'm slowing down in this direction. And let's draw one where we speed up. So we're going to be like, hey, 0 seconds, 1 second, goes 0.2 seconds, and then we're up here. So, you know what I mean? So in ones we're going real slow, and then in the next second we're going real fast. So in this direction we are acceleration in the x. And here we have no velocity in that direction, but now we got up to that point. So we must have an acceleration in the y. And you can see that, well, I don't know. Let's see what we can see. So if we do that and that, like maybe this acceleration, like look, this extra change in distance is causing the magnitude of this acceleration. And so we can say, hey, this one might be just a little bit more. So maybe this acceleration in the y is actually a bit more than the acceleration in the x. So hell yeah. So that's what we're going to do with our three points, and we'll just kind of get a rough estimate of. But yeah, I mean, I guess the take-home point is that we're going to find the change in these, so the change in this, and then divided by the change in time. So we said our original point, our next point is just a half a second away. So we have to take the change. The change is just 0.8, but we do that in a half a second. So we're going to have 0.8 divided by 0.5. That's the same thing as just doubling it. So we have 1.6 feet per second going in the direction of the ladder, and then 0.4 feet per second going in that direction. Cool. And then this one, now this one we're not going to take the difference between this and the original point B. We're going to take the difference between these. So 15 minus 8 is 7. So now we're going to have 7 times 2 is 14. But yeah, let's do this for real, and then get a kind of an idea of what the velocity and acceleration equation is in the direction of the ladder and perpendicular to the ladder. Alright, hell yeah. So, okay, so now what we're going to do is we're going to use this equation for velocity, change in position, change in time. And yeah, we're pretty much there. And then we're going to solve this problem using a smaller, because we went a foot at a time. So we really want to change the change in time to be like even 1,000th of a second. You could go 1,000,000th of a second. And, as long as your calculator can keep track of the tiny numbers, you're going to get a more accurate representative answer. Because if we went all the way to here, which was about a couple seconds, this velocity was way up there. You know what I mean? And that's not representative. If we really shorten this up, we're basically only traveling in the direction of the ladder. Well, no, we're traveling in the direction of the ladder and a little bit up. And that's kind of what we're finding. Most is in the direction of the ladder, but then we're getting definitely a component of the acceleration up. And like I said, the acceleration is kind of difficult to see because it's going to be the difference between the velocity vectors. But you need two velocity vectors to have a difference in velocity. So that's why we need 3 points. That's classically why you need 3 points. So we're going to say the velocity. So there's our equation for velocity. And I don't know, it's good to get subscripts. So we're going to be like 0, and maybe you just spell it out, 0 to 1. And we're going to take the difference of these. So again, it's change in position, change in time. Don't forget about that change in time part. Our change in time was 0.5 seconds. So we're going to have 0.8 minus 0 divided by 0.5. So, and the units on this are going to be, like 0.8 feet minus 0 feet divided by, and you can even say the change in time is 0.5 seconds minus 0 seconds. You know what I mean? And so, but there you go. 0.8 divided by 0.5 is going to be 1.6. And if you do this all at once, sorry about this, you're going to be 0.8 minus 0 divided by 0.5 I hat plus 0.2 divided by 0.5. I mean, basically 0.2 minus 0 divided by 0.5 j hat. So now we got 1.6 I hat plus 0.4 j hat, and this is feet per second. So there is our, let's write it again, velocity 0 to 1 is 1.6 I plus 0.4 j. This is feet per second. Alright, we're going to do the same thing, probably just, well no, I will spell it out on this one because this is a little trickier. 1 to 2, same thing, change in position, change in time. We're going to change our position by 1.5 minus 0.8. And then you could say our change in time here is 1 second minus 0.5 seconds. You can always do that. Or you can just say, hey, we're just taking a representative change in time of 0.5 and call it good. But this is your I hat plus 0.5 minus 0.2 divided by 0.5 j hat. So we're going to have, if we can do this, this is going to be 0.7, this is going to be 0.3. We're going to double it, so we're going to have 1.4, and then we're going to have 0.6. So hopefully we did that right. 1.4 I hat plus 0.6 j hat. This is in feet per second. Now we're going to find our acceleration. Our acceleration, definitionally. Now our acceleration is going to be a difference between the velocities. So we're going to have a difference between, velocity 1 to 2, to velocity 0 to 1. We're having this change in that velocity. So we're change in velocity, change in time. Here's our two equations for the velocity. And so we start with that later one. It's always, hey, where you, zero. If you're going from 0 to 1 second, you always take the position at 1 second minus the initial position. All right, hell yeah. So we're going to have 1.4 minus 1.6. And again, let's keep track of what the units are. This is 1.4 feet per second minus 1.6 feet per second divided by, and we're going to have, now this one, yeah, I think it might be confusing. Like, well, what is the representative time on this? Is this velocity taking at 0 and this velocity is taken at 2? Is there a change in 2 seconds? And I would say no, because here's your 2 points. You're saying, hey, the average velocity here happens right in the average amount of time, which is right there. And then the average velocity of this guy, the average velocity of, like, this 1 to 2, this is the average velocity 0 to 1. It's going to happen right there, and this one's going to happen right there. So this, if this is 0 seconds, 0.5 seconds, and 1 second, like our problem, this is going to be 0.25 seconds, and this is going to be 0.75. So the difference between these is still a half a second, 0.5 seconds. So, apologize if I said the word 2 seconds. I was thinking about just kind of our this example. I made a 1 second change in a 2 second. But for this problem, we just did a half second because, again, our velocity was 2 feet per second. We traveled a foot, so it took a half a second to do that. We traveled another foot, took another half a second. So this is a 1 second change. All right, hell yeah. So we have the change in velocity minus that change in time, and I guess I'm just going to write 0.5 seconds. Booyah. This is going to be our I hat, and then plus, we'll do it without units on this one, so we're going to have 0.6 minus 0.4 divided by 0.5 j hat. Let's see if we can do this in our head. This is going to be 0.2, but we're going to divide it by 0.5. That doubles it, so we're going to have 0.4. This is going to be 0.2. We're going to double it. This one's going to be 0.4. All right, so hell yeah. So we have an acceleration, and I'll just say the acceleration at B now is, because that's kind of what we're trying to find, the acceleration, at B when theta is 30 degrees. We're going to have 0.4 I hat plus 0.4 j hat feet per second squared. That's the units on it, feet per second divided by second. That's the units of acceleration, and booyah. All right, but we are going to take our time to explain again graphically what this acceleration is, even though kind of our picture's kind of bummed up. So here is this, at half a second, we're going to be right there. You know what I mean? So that's our point, over and up. Now at 1 second, we're going to be right there. So now what we're going to see is like, hey, look at this. So we traveled a farther distance in this half second than we did in this half second. So now we know that our acceleration must be back. So our acceleration in the I, and I feel like we didn't get the sign changes right. Yeah, my bad. Holy Toledo. I should have done this in my calculator. I'm glad I made a huge mistake. So 1.4 minus 1.6 is negative 0.2. So this really brings up the idea of like, hey, do things graphically, because it's almost impossible to mess up your sign changes. I mean, you can just see what's happening. If you can see what's happening, then when the numbers don't match up, you're just like, oh yeah, the numbers must be wrong. But yeah. So this is going to be a negative 0.2. Now this is going to be 0.6 minus 0.4. That's going to be positive. And that's what we're going to find. We're going to see that we're going to have an acceleration that way. We're going to slow down that way. Now let's see what happens this direction. So we're going to change by 0.2. But then if we go over here, look at this. So in this direction, we're going to go up to there in a half second. But now we're going to go up to there in the next half second. So we must be accelerating in that direction. You know what I mean? The positive j hat is negative I hat. And so that's what we see. You know, holy Toledo. Let's get a negative sign on there. And hell yeah. So we're going to accelerate back that way. And then we're going to accelerate up. And this should make sense because one thing that I showed is like, hey, let's take this thing totally vertical. And let's get this. Just kind of guess where that is. So, hey, point B is up there. But we know that even just after like a second, point B is going to be over here. So if point B is like right there, how the hell did it get back there? You know what I mean? If we have, it must have changed direction. So if we have a velocity component of B going this way, you know, in the I direction, the only way for it to get back up there is to have an acceleration component that direction, in the negative I direction. You know what I mean? To actually, hey, if we have velocity of B going this direction, and our endpoint's that direction, well, we must have slowed down that velocity, and guess what? We must have, at some point, made the velocity go that direction. Now, our change in our position right here, this thing isn't, this point B is not going to go that way. You know what I mean? So it is going to go this way. So all they want is the velocity at this point. So we do have definitely a velocity in the direction of this. And so hell yeah. But our acceleration is for sure trying to get back up to this point at some point. You know what I mean? But, I mean, depending on kind of the mechanism, sure, we could be accelerating this direction and then at some certain point slowing down. But based on this little mechanism, our acceleration is always slowing us down. You know what I mean? We're going to have our max speed initially, but we're going to slow down with that acceleration. All right, hell yeah. So I think we did it, and I think we really showed graphically like why the acceleration, acceleration's brutal. But I think we did it with the 3-point model. You know what I mean? 1, 2, and then maybe make this less, come up here, and then you got two things going on. You're slowing down this way, and then you have an acceleration in that direction and an acceleration in that direction. So booyah. And this, you had a velocity component in this direction. You know what I mean? And in this way, you never had a velocity. Well, you do. Like, you could say that, you know, you still right here do have a velocity component off the bat. But not when you, well, yeah, no, duh. You know, so let's go back to our position equation. So if we have our first position that's just right there, well, sure, we do have a velocity going that way because we changed position up into that part. So we have a change in position that direction, and we have a velocity this way and a velocity that way. The velocity this direction is bigger, velocity this direction smaller. But that's just representative of this axis that we drew. So the cool thing about taking any 3 points, like let's go back to our example before we finish up, is because like here, this is kind of like our problem where we have, you know what I mean, hell yeah, we have an XY axis, who cares? But if we just get these 3 points and be like, okay, this is 0 seconds, 1, and 2 seconds, you know, for our example. between here and here, our velocity component is just in this direction. You know, we don't have any component of the velocity in that direction. So how do we relate it to that? Well, instead of looking at this components, sorry it's sloppy, but because this point has a component this direction and this direction, what we're doing, and then our next point is there, we're just saying these are our 3 points, so let's just take this as our axis. You know what I mean? So this is going to be our axis this way, because we just want to see what's going on. And we can see that in regards to this axis, and if we go this direction, hey, this segment's bigger than this segment, so we must have acceleration this direction. And then we don't have any velocity this way, but all of a sudden we're up there, so we must have an acceleration that way. So that's kind of using the 3-point method. But yeah, I'm glad I caught myself, because hell yeah, if you have this axis, well sure, this velocity does have a component this direction and that direction. But guess what? Now this velocity for the second has a velocity that component and that component. So if we say these are representative, because this same change in time, if we say that these are representative, this is Vx1, Vy1, and this is going to be Vx2, and then Vy2. I shouldn't have labeled them like that. But what we're doing is we're saying, hey, look at this. This one's smaller than that one. So we must have an acceleration back that direction. And then let's compare these. It might be harder to compare, but hey, it looks like this one's a little bit bigger. Okay, sweet. So bigger minus smaller, we're going to have, you know what I mean, we're going to have an acceleration that way. And so that's kind of what we have here. And so that was a pretty good representative of what's going on. You know what I mean? And so that's kind of a cool way to do it. I think what's going to get confusing is you're just like, well, aren't these just positions? How from these positions did I put a velocity vector on there? But because it's just... that's the one that's proportional to the position. All I'm doing is taking the position and then dividing by time. So I guess what's interesting about this velocity vector does not have a magnitude that's equal to this distance. So if I actually draw this vector on here, and maybe this distance is, like what were these? Yeah, let's say this distance is just like a half a foot. You know what I mean? So like 0.5 feet. That doesn't mean that the velocity is 0.5 feet, because that's not the units on velocity. So if this is 0.5 feet, this velocity in a half a second is going to be 1 foot per second. So this shows that you can have a velocity vector, and you can visually draw it the same dimension as the distance vector, but all you're doing is just, if you're going to do that, it just makes it representative. You know what I mean? If you make this velocity vector in the same distance as your position vectors, then they're just all scaled. So then you can visually see that this velocity is bigger than that one, this velocity is bigger than that one, and that'll help you visually to get that acceleration component. Alright, hell yeah. So I'm actually going to stop here, and I'm going to make a separate video, because this is a starred problem that's kind of fascinating. But because what we would do is we would just have an ident. The first thing I do is do that same thing. Do a half a second. Actually, I did a tenth of a second. So I made this go 0.2 feet. Because if you make this go 0.2 feet, you know what I mean? And like this distance is actually like 3.5. So then this dimension now becomes 3.3. So even if you do a smaller change in time, and I did a change in time of, what is that, a tenth of a second, 0.1 seconds, you can still get a visual, visually it still kind of makes sense and the numbers make sense. And then we can figure out the angle. Because if this was a 30-degree angle, look at this. This angle got steeper because, like, make it extreme. Hell yeah, this angle is almost 90. You know what I mean? So this angle is going to increase, and that's the part of the problem that I didn't even tackle, is the increase in angle. But we can tackle that in 2 steps using a change of time of 0.1 seconds and then figure out the change in angle. I think it's like 3 degrees in a tenth of a second. And if it is, if it is 3 degrees, I don't know if it is, but if it was 3 degrees in a tenth of a second, that's going to be that's 30 degrees a second. You know what I mean? So that would be the change in angle. The angular speed would be 30 degrees per second. We don't do angular speed like that, which is a bummer, because if we did angular speed like this, we'd have a better representative of it. But let's go back to what a radian is. If you have I would do this. If you have a circle, divvy it up into 6. The other thing that I would do is do a 90, go up to a 60, and say, hey, that's 1 radian. And if you know at least that angle is 60, then you can be like, okay, 60 degrees is 1 radian, so 30 degrees has to be a half a radian. And if we're going to do 30 degrees per second, we're going to do 0.5 radians per second. So it's just good to get just a ton of mental math and be like, oh, I know what a radian is, so I for sure know what a half a radian is. That one you want to burn into your brain. 1 radian, 60 degrees, half a radian is 30. No, it's not exact, but it's close enough. Alright, hell yeah. So, and no, we're going to do that from this drawing. You know what I mean? Because even if we come in right here, does this look like a 45 degree angle? You know what I mean? Like, does it? I have no idea. Like, I think it is. No, it looks kind of steeper. How about this angle? Does that angle look like 45? That almost looks like more like 45. You know what I mean? So, but a little bit less. But that's fine. I'm going to say, maybe our angular speed is going to come out a little bit high. But that's going to say we have we had 45 degrees here minus 30 degrees to start. And so we had 15 degrees in a half a second. Oh, well, hell yeah, that's 30 degrees. So even though I remember the calculator calculations of 3 degrees for a tenth of a second, you know what I mean? And it was a little bit more. It was like 3.3. So there you go. So yeah, 30 degrees. So our angular speed is about 0.5 radians, per second. So now we know our angular speed is 30 degrees per second and 0.5. But this brings up the take-home point of like, this is my method to do any problems. Even if the textbook says, hey, we're going to spell it out for you and do all these crazy steps, it's just like, I don't like to do problems that way, but I do want to learn how to do all the crazy steps because then it can help me down the road. But I would still, any problem that I try to do, why not pretend like it's 20 years in the future and you have forgotten all this stuff? Like, what are you going to do to tackle this? If you're on a desert island and you still want to do some dynamics, but you forgot all the equations, you know what I mean? And hell yeah, you could still do some dynamics. So that's pretty sweet. I think we covered it. I guess the only thing that I kind of want to finish with is that instead of doing like 0.2 feet, you know what I mean, just a small change, we're gonna do like even tinier. As long as your calculator can handle it, you can do a change in time. Like sometimes I'll go up to, like for this problem, it would be way too stupid. I wouldn't like it because I would lose all touch of the numbers. But you could do a change in time of 1/10,000th of a second. I like a thousandth of a second. Sometimes I'll start there, and even that, a thousandth of a second, you're gonna lose all track of like this is just gonna be so tiny. So if this distance is like 3.45 feet. And then this change in distance, you know what I mean, it goes to there. Well, now this distance is going to be like 3.45 minus like 0.0004, you know what I mean? And you're just like, oh, like it's not going to, there's no feel for the problem. But if you do that, and then you take this this tiny distance right there, and then an even tinier the same tiny amount right there, you're still, oh, this is really cool. You're still like, hey, this distance is going to be bigger than that distance. And so you're still going to have an acceleration component. And that tiny acceleration, you're going to divide by 1,000, and that's going to get it back to that original number. But it's going to be hella accurate because they want the velocity at this precise
point, they don't want the velocity up there. And we already chosen, to move that way and that way. And so now we're more getting a representative of what the velocity is over here and not the direct velocity at this exact point. So if we tighten that up, and sometimes I'll even do the problem in reverse, because if this is sliding this way at this 2 feet per second, well, it must have started, it's like 1 second ago, it was 2 feet this way. Does that make sense? So then a thousandth of a second ago, it was just over here, based on that speed. So that's going to be, and I think I'll do this problem that way. If we want a hella accurate answer, then I'll start with 100,000, and then we'll move this way, and then we'll have this 0 point. We already have that, and then we'll move this way. Okay, hell yeah. But that's going to be for another video. So thanks for joining me on this one, because this was sweet. We just used some little paper and then just kind of drew it out to scale, and we got pretty accurate. So thanks for joining me, and guess what? That's a video.